substance. All right, so we mentioned the word state. We'll also see physical state or phase to represent the same thing. And your book uses all three of those terms when it describes the state of matter, or the states of matter. So we're going to be taking a look at how we can describe the changes in physical state and what sort of energy changes accompany those changes in physical state as well. We're going to introduce some terminology to help describe those changes. So how does a substance change state? In other words, for example, if I have a solid sample of ice, how does it turn into a liquid? What do I need to do to it to turn it into a liquid? Yeah, so I need to provide some sort of energy. So there needs to be an energy change, right? So changes of state occur when the substance is subjected to energy changes. All right, and we're going to be taking a look at our three physical states, the transitions between them, and the energy associated with those three transitions. Or actually, there's more than three transitions. I'm going to redraw this here on the side, because I think my diagram is a little bit better than theirs. All right, so we're going to have our solid. We're going to have our liquid. And we're going to have our gas. Right, that's the three physical states or phases of matter that we talked about. So, we mentioned as the example there, going from a solid to a liquid. So going from the solid to a liquid, we said that we need to provide some energy to it, right? So in other words, we need to heat the solid ice up, for instance. So we can say this needs or requires energy. And what is the name of the process when something turns from a solid to a liquid? So if you're ever confused about these transitions in the three physical states, go back to the one thing that you do know that exists in all three physical states, which is H2O, water. So solid ice to liquid water, the ice melts, right? So melting is the name of that process. And there's a technical name that we give to it called fusion. Right? And that requires energy to take those solid particles and start to separate them now into the liquid state. Let's continue our cycle here. So liquid going into a gas. So liquid water, and I want to turn it into the gas phase or the gas state. Right? That process, will it require energy, or do you think energy will be given off if I want to turn liquid water and I want to turn it into the gas state? It's going to require energy. I need to provide energy to it. So this is also going to require energy. And that process going from the liquid to the gas is called vaporization. And that's because gas, the physical state of the gas, is oftentimes referred to as a vapor. So water vapor, for instance. Right, so vaporization going from the liquid to the gas, and that is going to require energy. in some cases, we can go from the solid directly into the gas and skip the liquid phase altogether. Right? So if you have a sample of solid ice, we can heat it up. It turns into a liquid. We can melt it into liquid water. And then if we provide it with more energy, we can turn that liquid water into steam, right, through vaporization. In some cases, if the conditions are right, we can go from the solid directly into the gas. And that process, do you think, is going to require energy, or is it going to give off energy? From the solid to the gas. So solid, particles are like this. The gas, the particles are like that. So I want to go from the solid to the gas phase. I'm going to have to give it a bunch of energy, right? So the particles can absorb the energy and start to move around. So this is also here going to require energy. And that process going from the solid to the gas phase, skipping the liquid phase altogether, is known as sublimation. All right, and a good example of where sublimation happens would be if you have something like dry ice. Has anybody worked with dry ice before, or used dry ice for different things? So if you have a block of dry ice and you just let it sit out on the table, what does it turn into? Is there a puddle left? Like normal ice? No, it goes directly from the solid to the gas phase, right, and skips the liquid phase altogether. So it's undergoing sublimation, right, and that's due to the nature of the dry ice itself, which, by the way, is solid carbon dioxide, is what you have in dry ice, and it's really, really, really cold, right? You wouldn't want to hold it in your hand without any protection. All right, so we've seen these transitions from the solid to the liquid, melting or fusion, energy required, liquid to gas, vaporization requires energy, and then solid to a gas, that's sublimation, that requires energy as well. The opposite processes can also happen. So we're going to take these transitions and essentially flip them, which means the energy changes are going to be flipped as well. All right, so if I go from a gas to a liquid, right, if going from the liquid to the gas required energy, then going from the gas back to the liquid, which is opposite, should do what? What energy change should we associate with that? Energy would be lost or given off in that process. All right, so energy is released. And the name for that process going from a gas to a liquid is called condensation. All right, condensation happens all the time. It's raining today, right? And rain clouds form because of the condensation of water vapor as it rises in the atmosphere. Eventually, they lose energy, they give off that energy, and the droplets get closer and closer and closer together. They start to clump together. They eventually form clouds, and if the droplets get big enough, then they fall out as liquid precipitation, which is the rain. You get wet as a result of that. Going from the liquid to the solid, right? Again, think about water going from a liquid to the solid phase or solid state. What would be the name of that process? Liquid to solid. That would be freezing. And then would energy be required or released in that process? Energy is going to be released, right? Is the opposite of melting or fusion. And then to complete our circle here, or our triangle, I guess, we saw it going from a solid to the gas is called sublimation. That required energy. We can also go from a gas directly back into the solid. Right, so that process then should also release energy. And the name given to that process is called deposition. All right, so I tried to color code my energy transitions here. Red, energy is required. Blue, energy is released. It's the same sort of color scheme in your textbook. But your book doesn't have I don't think, a good of a layout as mine. Your book actually looks a little bit better because it's professional and it's typed. Mine, you kind of have to navigate through my chicken scratches. All right, so with these three physical states, the energy changes associated with them, as well as the name for each of these energy transitions or the phase transitions, you need to know those. Right? If I tell you something undergoes vaporization, you need to know which physical state it starts off at and what it becomes if something undergoes vaporization. Something undergoes sublimation, you need to know that it starts off as a solid, turns into a gas, and that process would require energy or heat energy. All right. Couple things here just to sort of tie up some loose ends with our triangle, our circle. So a couple terms that often get thrown in there that don't necessarily mean the same thing. The first one is evaporation. And when something evaporates, evaporation happens at the surface of a liquid only. So for example, if you have a beaker of water or a glass of water out in the open, right? Remember in the liquid phase, the particles can slide past each other. And at the surface of the sample here, of the water in this case, you have nothing preventing these particles at the surface from breaking free and going into the gas phase. And if they do that, if it's happening at the surface only, that's called evaporation. And over the course of time, as more and more liquid turns into the gas phase through evaporation, the level of the liquid is going to drop and drop and drop. Right, so evaporation is only happening at the surface. Boiling, though, which is what happens when we provide some heat to this, boiling happens throughout the entire sample itself. So at the boiling point, the entire sample gains energy to turn into a gas. So when you boil something, you actually see gases being produced or formed throughout the sample. So you stick a Bunsen burner under this beaker of water, you'll see bubbles being formed throughout the entire thing. It doesn't just happen at the surface, it happens throughout the entire sample. Because you're giving even the particles that are way down at the bottom enough energy that they start to break free from each other and turn into the gas phase. All right, so evaporation is just at the surface, boiling happens throughout the entire sample. That's the main difference there that you want to keep in mind. All right, let's take a look now. Let's try to put all of this stuff together and take a look at what would happen if we have a sample of, let's say, ice, and we heated it continuously, starting off at a really, really cold temperature. And we're going to plot this on a graph. And what we're going to measure is the amount of heat added on the x-axis, and then we're going to see what happens to the temperature. on the y-axis. I'm going to measure that in degrees Celsius. All right, so we're going to start off with solid ice at negative 40 degrees Celsius. So pretty cold, really, really, really cold. So it's really cold ice that we're dealing with. So we're going to say down here is negative 40. I know it's not the origin and it's not 0, but for the interest of simplicity or time here, we're just going to say that this is our negative 40. That's our ice. And we're going to keep adding heat to it. So as we add heat, what we're going to see is that the temperature starts to increase. So we add heat to the ice, keep adding heat, the temperature starts to go up and up and up and up and up until we get to a point where we add more and more and more heat, but the temperature remains constant. So when we get to that point, what we actually will notice is that that temperature corresponds to 0 degrees Celsius, which is the melting point. Of water. So the ice, we provide heat to it, the temperature starts to increase until we get to the melting point. And even if at that point we provide more and more heat to the sample, the temperature does not change. Keep adding more heat, more heat, more heat. Eventually we're going to get to the point where all of the ice has melted. And then we keep adding more heat, and now the temperature of the liquid water is going to increase. So we keep adding more and more heat to our liquid water now. The temperature of the liquid water starts to increase, increase, increase until we get to a point where the water starts to boil. And at that point, the temperature remains constant again. And the boiling point of water is 100 degrees Celsius. All right, that's our boiling point. And if I keep adding more heat at the boiling point of water, we'll see that the temperature stays constant as that water turns into the gas phase until all of the water has boiled. And then if we add more heat to it, now we see the temperature of the water vapor or the steam starts to increase. And this is what you would see, right, for in the case of water. We start off with really, really cold sample of the ice at negative 40 degrees. We start providing heat to it. The temperature of the ice starts to increase until we get to the melting point where it starts to melt. And at that point, any extra heat we provide goes into actually melting the sample. It doesn't increase the temperature. So we keep adding more heat until all of the ice melts. All we have now is liquid water. Any extra heat we provide at this point goes into increasing the temperature of the liquid until we give it in so much heat that it actually starts to boil. It turns into the liquid phase. Any extra heat we provide here goes into boiling, turning it from the liquid to the gas until we converted all of it to the gas phase. Extra heat here now goes into increasing the temperature of the gas H2O. So you'll notice that on the graph that we plotted, there are two regions that are flat, that are plateaus. Right, and these regions here in purple correspond to phase changes. And at the phase change, either going from the solid to the liquid or from the liquid to the gas, the temperature does not change. So this graph that we plotted, even though it does not necessarily look like a curve, it is actually called a heating curve. And this is specific for water. Right? So it shows you the temperature change as a function of the amount of heat that we add to the sample. So it's not a straight line. There actually are regions where we have plateaus where the temperature does not change, and those correspond to the changes in state or the changes in phase. So when you look at one of these curves, you can quickly identify where those are. All right, so this is a heating curve. We can actually do the opposite, and we'll end here. We can start off with steam or water vapor in a very, very hot temperature, and then cool it down. And we see the exact opposite of what we just did. Right? So this cooling curve is just the heating curve in reverse. It's a mirror image of it. Right? We still see the same two plateaus here that correspond to the different phase changes.